There's only a couple of us here in the room, so we can make this really simple and informal. I work primarily with depth cameras. And so this talk is going to be kind of, it should be nice because it's mostly eye candy. We're working on some applications and research and stuff like that. And so I thought I would present some of the places that I think this new technology is going to be able to, the doors it's going to open up for us. I could use this. Okay, so who here has heard of the Kinect? I think this is one of the really hot things out there right now, and I think Microsoft was pretty smart to take themselves in this direction. It's something that's really going to differentiate them from Apple and such. But who's heard of PrimeSense? PrimeSense is actually the technology that's inside the Kinect. Little did you know. What about PMD? Or Mesa? Or Kinesta? Well, all 5 of these companies / products all have one thing in common. They're all in the depth camera business. So this Kinect, thing that Microsoft is doing is actually just the front end of something that's really going to be hitting the market and making itself a stake in the technology that everybody is going to consider normal in their life. We consider having a webcam on your phone or your desktop or your laptop something that's just regular. I can Skype with someone, no problem. And they hope to make depth cameras something that are just normal, something that is ubiquitous into the general population. So the things that are presented in this talk are things that are interesting because they're going to be so widespread. And as it is right now, the Kinect is selling for $150, but given a larger audience and such, I really think these kind of depth cameras can be sold for much less. Okay, so one of the cool parts about what we're going to talk about today, or do today, is that I am going to show you a live demo of a depth camera. So I figured since I work in this space, in this lab, we can just pull out the camera we have. Now this camera does not cost $150 like the Kinects. It costs $10,000. But that saying, it's going to be one of the highest quality cameras out there. Actually, I think this is still one of the highest resolution cameras that you can get. Oh, is that good? Yeah, it's on. The color coding on here is simply just a false coloring, so you can more easily detect, so you can easily see the depth. So here we go. This is live output from a depth camera. In this case, I think pretty sure blue, darker blue, it's farther away, and then as it gets redder, it gets closer. And then there's a certain point where you can mess it up. So the technology this technology here is produced by PMD Technologies. They produce what's called a time-of-flight depth camera. So there's 3 major, there's at least 2 major ways that I can think of to get this kind of fast depth camera video rate technology. One of them is the way that Microsoft does it in Kinects, which is actually where they project a structured pattern of dots onto a scene. I don't know if you've ever looked at some of the hacks online, but they basically project a structured pattern onto the scene and then use computer vision algorithms to try to infer the depth from the distortions of that known pattern. Whereas this technology is actually using time of flight, where it's actually sending out infrared radiation from these 2 side things here. And so if I go like this, it's going to cause lots of problems because that's all of its illumination. And then it has a CCD kind of array that actually calculates the time that it takes for the light to come from this sender back to the camera for each pixel. And so That's why you get a pretty high quality. And now, since I can't really do both these at the same time, I'm going to go to a recording so that you can see because another cool feature of this is that the software that comes with this is actually three-dimensional. But since it's hard for me to do both at the same time, I'm just going to load up a recording. The recording was in case I couldn't get this to work on the fly. Okay, so here's exactly the same thing as you saw me just working there, a live demo. But now it's just a recording. So I could probably set this again. So okay. So one of the cool things about this, though, is, as I said, you can see the three-dimensionality of the picture. So what this is simply doing is that for every pixel, you can determine a 3D point in space. And then it's color-coded, as I said, just to give you an easy sense of the depth. So now, this is, as I said, one of the highest quality depth cameras out there. One thing is, though, it is lower resolution due to the fact that each pixel is actually calculating this depth every frame. Takes a little more space than the average CCD pixel would. And so it's about a 200 by 200 resolution camera right now. So that makes what, about 40,000 points? So every point here, the Kinect does the computer vision calculation, so it has a higher resolution in a sense. But that's just part of the difference in the technology. So some of the things to point out is, one, there's actually a decent amount of noise that happens with this kind of camera right now due to edges. One of the reasons is if you have the light coming off here, the infrared comes off, hits an edge, most of that signal is going to go in another direction. So the amount of signal that comes back is low. The other problem is that each pixel here is going to project onto some finite space. And so if there's an edge that runs through that, it's going to measure both the distance of the foreground and the background. And so it's just doing it measures the distance like probably thousands and thousands of times to get each frame to get an accurate measurement. And so it's going to average between the foreground and the background. And so you get a lot of pixel mixing there, or background and foreground mixing, which is what you see here. So let's cancel the demo for now. And if you want, I can show you. I can do this demo live a little bit more later. But I figured that would be the most interesting part of the talk so far, or in general, just because you might not have been able to jump into, get your hands on a Kinect and hack into it yet. So the technology, as I said, I was working with is this PMD technology, and here's how it actually works. So we have the camera, and as I said, it sends out a modulated pulse. That pulse comes back, and here's the basic way it calculates it. It calculates a cross-correlation function, which is done in hardware, but this is the conceptual mathematical idea. So you have the sent signal and the received signal, and the cross-correlated signal is some kind of sinusoid like this. And I'm not really familiar with the dynamics, but they basically sample it 4 times a cycle, and from that they're able to determine the phase difference. And so the time-of-flight camera like this works on phase differencing. And so then the difference of phase between the sent and received signal is going to give us that time delay. One of the drawbacks to this is the aliasing. So if I were to turn this camera around and point it towards the back of the room, it would be great up until maybe the fourth or fifth row. And then after that, it's all of a sudden kind of starts to wrap around because it's aliased. I think this camera is for about 7 to 10 meters before it starts to alias. I'm not sure exactly what the settings are on it. But one of the nice things about this type of technology over the one that the Kinects use is that it gives you more information as well. So you get both the phase difference, which gives you the time difference and the distance, but you also get two other values. One is the amplitude, which is basically a measure of the signal that's been received. It's a measure of the correlated signal that's been received. And then the offset, which is basically a measure of the infrared intensity value. So the base value that wasn't a part of the modulated signal. I'll show you how those can come into play. OK, so as I said, I really just wanted to give some flavor about the depth cameras today and talk about some of the applications that my research group, which is under Min-Do, is working on. One of the very first ones that we looked at, well, I didn't look at, but the group looked at, was this idea of segmentation. So here is just that intensity information played in a video that came from the depth camera. The first and most obvious application of depth is, hey, look, I'm standing in front of you, and maybe there's some complicated background behind me, but you want to segment me out. And you're like, well, that's always been a difficult problem. In TV, they'll put a blue screen behind you, makes the problem a lot more simple. But all of a sudden now, you take this depth camera and you throw it in there. So in this case, it's a little bit simple because the intensity of the foreground's much brighter than the background. But if I were to attach a color camera to this, it would not be as obvious. But as we saw earlier, that given a little bit of depth, now it's very obvious. I mean, you can look at the color here and see, but if you simply put a thresholding plane in the depth camera view, you can basically get a mask that says, this is the foreground, that's the background. Now, there is some noise, and so as I said, you can use that amplitude information. So here's that amplitude, where I use that amplitude information, and I basically said, I'm only going to now consider pixels of a certain confidence. So you can also use that information in the processing. Gives you another sense of segmentation. And then here is that intensity image now trying to just take out the foreground. One of the drawbacks of time-of-flight depth cameras is the inability really to do hair very well yet. The reason is that hair tends to absorb a lot of the infrared, causing it to give a very low signal back. I mean, it can measure it, and you can get a certain sense, but it's often very noisy and can cause a lot of artifacts. But here's where a lot of the depth camera is really being used right now. I want to control something with my hands. Oh, look, now my hands are completely segmented from everything else, and I can easily track those two major blobs in the screen, and now I'm driving a car. Or now I want my movie to stop, or I want you to go to whatever number. So that's what you take a normal image, and all of a sudden you can easily extract significant pieces of information out of it. Why? Just because it showed up a little bit more in front of everything else around it. So there are some challenges with this particular technology. One is that it is very low resolution. So pumping this into a color camera viewpoint does cause a lot of artifacts. Specifically, there's artifacts around the edges. As I showed, that there was edge noise. So if you try to superimpose that onto a color image that's much higher resolution, the color edges tend to fluctuate a lot based on that noise. And then there's also a certain movement noise that just occurs. And we haven't quite classified that, or I don't have a complete understanding of that, but you can definitely notice it. But the possibilities are really, really important there. Just in the general natural user interfaces, but also in a lot of robustness to some of the computer vision algorithms out there that try to, if they could center in on what they wanted to, their algorithm would be so much more robust. But the problem is they have to try to guess that this is what they were looking for, not that thing over here that kind of looks like it in terms of pixels. So as I said, you have a low resolution depth, but you have a high resolution color. So some of the research out there is to basically enhance the depth with the color map, basically trying to steal the information from the color and use it to boost up the depth. So this is a paper that someone was reading in my lab. There's also current work working on in my lab, but I couldn't snatch any good pictures from him. The basic idea, though, is you have this low resolution, you have the high resolution video, and you try to combine them together. It's not quite as simple as you would hope it would be. One of the reasons being that, so the base assumption is that when there's an edge in the color, it might indicate an edge in the depth. And so you try to use the similar edges. That does lead to some problems, though, where there's some texture that you copy from the color information into the depth that you didn't want. So another application is where we then try to use the depth camera in order to increase really the ability that we'd have with color cameras. So there's a lot of work out there on basically freeing up the viewpoint of a camera. Some of the methods were to take a large array of color cameras and then try to interpolate between the color cameras to give you kind of a free viewpoint. But in this sense, we're now considering only a small number of color cameras and a depth camera, where you had some scene in front of you. And the idea being that, given the setup, you'd like to be able to actually create a virtual image somewhere in here, somewhere in between the two color cameras, based upon the depth information you get. And we were able to do some of this, and it was we displayed a little bit in an IEEE signal processing magazine. And the idea being here that we took a left view and a right view of the subject, and then we basically projected that depth information onto the color images, used the color images to increase the quality of the depth information, and then reprojected the color information back into a virtual viewpoint. Well, in this case, the virtual viewpoint actually had its own camera. So here's what the actual camera was at that position, and then here's what the virtual viewpoint was. And then the nice thing about it, as you can see, is it's a really good virtual viewpoint. There are some artifacts around the edges. Again, that's mostly due to the noise, which is one of the drawbacks right now. A lot of the applications that I'm showing you are really promising, but the low resolution and the noise of the depth camera right now are definitely something that's keeping it from exploding into consumer-grade applications.
Was that information obtained from an intermediate view, or?
Yeah, it was just like this setup here. Just like this setup here. So there was a color camera on one side, another color camera, and a depth in the middle. And then the virtual viewpoint was like, so basically there's three color cameras, and there was a virtual viewpoint right here. But we didn't use the virtual information for any of the processing, just as a ground truth. Yeah, if you have any questions, I didn't include a lot of the details, technical details, but if you have any questions about them, just feel free to stop me, and I will do my best to explain them. Okay, so one of the major applications of this, as we were looking at it, was to correct the problem of video conferencing, where in general in video conferencing, you need to look at the screen, which has the person's face on it, but your cameras need to be positioned off screen. And so there was this, I don't know if you've ever used a video conferencing system and noticed that problem where you're kind of looking either at the screen and then the other person doesn't feel like you're looking at them, or you're looking at the camera and you don't really see the screen as well. And there were some articles that showed that, that's actually a decent problem psychologically, because if someone isn't looking you in the eyes or looking at you when they're talking to you, they might just be lying or they might be trying to hide something. And so we were hoping that possibly adding a depth camera to that setup might be able to do a real good job of changing the viewpoint such that you are looking at wherever the person's face is. Much better than a lot of the hacks that are out there. There are some hacks out there that just kind of try to orient the plane differently or do something, but this is really creating a virtual viewpoint. And finally, in the combining depth and color. The application is really trying to augment color with this depth information. So the real application that we looked at here was the idea of relighting. Taking an image and trying to relight the image realistically is pretty much next to impossible. I mean, you can do some like histogram things to like balance it out or whatever, but to really add some kind of virtual lighting source to the scene, you either need to do, one, capture a large number of images of that scene with different illuminations, because they showed that illumination is additive. So if you capture the same scene with a large variety of illuminations, well, then you can change the illumination. But just to capture the scene once and try to change the illumination is a very difficult problem, mostly because illumination is very geometric, 3D dependent. And so now adding this 3D information into the process, it really opens up the door to making this possible. And so here's a simple video that we created. And all this was took a depth image, extracted out the normal information from that depth image, basically attach a normal map to the same image. And then based on those normals, you can do the computer graphics techniques of adding light, as they would to any kind of computer graphic model. And then the real trick that's difficult and wasn't quite pushed through all the way in this topic is then being able to take this added light that you got from these normals and then putting it realistically with a color image. And some of the challenges with that, though, are still the idea of recovering the intrinsic color of the object in front of you, because you can have illumination changes that make this part of your arm look darker than this part, but they're the same color. But again, it's difficult, but I still feel like with this depth information, you actually might have a better chance at recovering the intrinsic color. Also, just getting rid of those, the previous illuminations. And then the major issue in this area still, though, is the depth, or the noise in the depth image. You'd like to be able to take one image and use it, but the noises around the edges cause a lot of artifacts. And then now this is the topic that I'm working on most vigorously right now, is really the idea of using this depth information over time. So in general, to use color information over time in a video sense, it's sort of difficult. If you need to track some object in color, you're tracking something in 2D that's really 3D. So as soon as it starts to rotate, or if it's moving in plane, well, then it's relatively easy to track and accumulate knowledge. But as soon as it starts to rotate or changes plane, you basically have to start trying to estimate the 3D parameters of the 2D object you're measuring. But given the 3D information right off the bat, we would like to basically try to capture that consistent 3D geometry. And so here's just some easy ways to show it. So if you're wondering, if I took one depth image and I were to just project it into 3D space, here's kind of what it looks like. Just naively putting a mesh on top of it. And you can see there's a lot of noise in it. But here's the real idea of what I wanted to show. So here's one frame that I've tried to clean up a little bit, which you get a good sense of what you're looking at through this frame. But if the object were to be rotating, or the camera rotating around the object, and we were to try to accumulate this knowledge, we could get something that looks closer to this, where now there's a lot more filled-in information, and the idea being that we want to basically just take this information that we've acquired, and all these points were acquired in probably 3 to 5 seconds. So I mean, this is just a very small amount of data that we're trying to look at here, compared to how much data we could get. And there are some artifacts still even in this point cloud, in the sense that it's still a difficult problem to register successive frames, or the entire frame set to itself. But the idea then being, okay, so I can get all of these points, but can I put them in some kind of model? Can I build some kind of model over time that utilizes all this information, but can kind of do a real-time model, such that I have some model, and I'd like to basically take a new data set that comes in from the camera and somehow add it to the model. And maybe it's some form of what was spoken in the last talk kind of intrigued me, of starting with a really rough model. So the nice part about the depth camera is that you have so much information. I think typically a lot of problems consider only one image, and you're stuck with that finite amount of information. You have to do the best you can. But the idea being here that you're getting information over time, and the information is relatively consistent. And we're limiting ourselves to rigid objects at the moment. But the idea being that you can look at something, and when you look back at it the next time, it's going to be the same thing. It's going to have the same structure. And so you can use those redundancies to reduce the noise. I think that's about. Okay, so here was the outline of what I'm trying to do right now with the depth camera, or the depth over time, is that we get the information, 3D information. We need to register it. Then we're determining some sort of way to integrate the knowledge. Right now I'm using what's called implicit moving least squares. So it's a moving least squares approximation taken from the graphics community. And then trying to figure out some way to represent that. And the moving least squares gives us a representation that's basically a signed distance function. So every point in space that we calculated at, we can get an approximation to the distance to the surface. And part of the research now is to try to link all this together. So you can just take depth data and just kind of push it through to a representation. But the idea then being that, okay, so I'm building some representation. I want to bring it back so that I can do better registration and better integration. And that's really the key part of what I'm working on right now. So those are the major things, the applications that we're working on in our lab that I wanted to display today. That the segmentation, really the incorporating depth and color. I only touched on the three applications, which was trying to increase the depth through the color, trying to change the viewpoint, or trying to augment the color through the depth. But there's still a large untapped well of applications there that's what kind of really interesting about this depth camera, is that there's a lot of possibility, and it's coming. And here's some of the places that what we're going to be able to do, I think, in the future, are what we really need to do. One is we need better signal processing to improve the depth. It's going to give us more natural interfaces, and we're going to get more virtual control. And what I really hope is that we get to the future where we'll be able to do a lot better 3D modeling of complex objects and shapes. I think that's going to really open up the doors for novel applications that we just can't even imagine right now. I think the concluding mark out of all of this, though, is that this technology is coming, and I really believe it's going to fundamentally change the way that we look at a lot of simple 2D images and the way we process them. Thank you. Any questions?
You gave a lot of examples of consumer electronics. I'm curious if you could speculate on applications to industrial uses, or how about automobiles?
Oh, yeah. I mean, right now, a lot of what this technology is used for is in terms of those more industrial applications. Either if you wanted to, be checking your products for their size or shape, or I think even this camera, this company has a demo where they installed this kind of depth camera into the front or the top part of a car, and we're able to do better navigation. And I don't remember the exact details, but I mean, there are other people who are looking at this in terms of obviously robotics. I mean, the idea of just being able to map out a room in terms of robotics, the ability to to be able to look in front of you and be like, oh, there's a big object that's coming right in front of me, because I mean now you know how far away it is. I mean it's not like a picture was. You actually have a sense of how close something is coming to you. Yeah, I mean I guess I'm primarily looking at this in terms of consumer electronics. That's kind of the people who are funding me kind of are pushing me towards the large scale kind of uses. But there are obviously, I mean, this technology is definitely going to affect businesses and the way they manufacture things and stuff like that.
So you said the images that you get are kind of low resolution.
Yes.
So I'm guessing the ones in Connect would be even lower resolution ones.
Well, they're not low resolution; they're lower quality.
Okay. So do they? I'm just curious. Do they just use depth cameras, or is it like they have like a live video also running, and they try to?
Yeah. So the way the Kinect works is that it has two cameras. It has the color camera and it has the depth camera, and they're placed so close together that it's a relatively trivial hack to superimpose them on top of each other. So that's kind of the way it works. It's why it has both color and depth, which is a really big advantage for it. But the problem of actually taking a depth camera like this and an arbitrary color camera and integrating them together or being able to put them together is definitely not a impossible problem, but is actually is at this moment a relatively unsolved problem. But as I said, the Kinects use a different technology, and so they can have. So the way their camera works is that they project those structured light points, and they actually have an infrared like normal CCD camera that can have a much higher resolution that tries to look for those structured light points, and so based on that, they can get a higher resolution output. But in what I've seen, I mean, I've worked with the same cameras that were in the Kinects, and the quality is not comparable. It's not really the same as this one. Like this one definitely gives you much better sense of like distance and space. Let's see the what?
Feature size smaller.
Yeah, I mean the Kinects is good though in a certain sense. But one of its best uses right now is segmentation. That's if you want any proof of that or any kind of like a heuristic, Microsoft used PrimeSense technology to make their Kinects, but they recently announced that they're going to buy Kinesta, who makes a camera like this. So in general, I think most places are going to go towards this time-of-flight technology. This camera in front of us is $10,000, but I have seen a device that was roughly about that big, made by the same company, that I think they're projecting for $100 to $200. One of the big things about this camera is it has this really nice lens on it and has these really big LED infrared emitters. Yeah. So the amount of output it can throw, the amount of infrared it can throw into the scene is a lot larger, and therefore it can get a better signal to noise ratio coming back to the camera. So that's one of the trade-offs. You know what I mean? Yeah, you can put a really tiny emitter and the same camera. I mean, basically has the same camera, but it doesn't have the same lens and has a smaller infrared emitter, and so you start to lose quality. So we're working with this camera right now, basically being like, someday, I bet all cameras will be at least this quality. And we're trying to see what we can do with that one. Because even with this higher quality camera, it's still very difficult to get things that don't have a lot of errors.
Okay, I think we're out of time.
Yeah.
Let's thank Daniel.
If anyone would like, I can put this demo up out in the hallway later and we can play with it.